So in the last video I finished talking about the applications of the physical properties of waves by explaining about the stationary waves. So as the last part of the topics of waves, I will be explaining you about the concept of the application of sound. Now sound is also a type of wave. I explained to you that sound is a longitudinal wave in my first part of video on waves, when I introduced waves, the different types of waves. So sound is a wave, and we have some applications of sound in the case of waves. Now in the case of speed of waves, I explained to you that the transverse wave on a string is equal to V equals root T over M, where T is the tension and M is the mass per unit length. And in the case of sound waves in a gas, you can say that is equal to V equals gamma P over rho. So gamma is actually the ratio of molar heat capacities. So that I'll explain in the videos of heat. Right, so that's the next topic on physics, the topic of heat. So for now you will know that this is approximately, for air you know that this is approximately equal to 1.4, and P is the pressure and rho is the density. So if you know these values, you can take this ratio and then take the square root to find the velocity. And also by PV equals nRT, you can say that you can substitute for P and you can say V is equal to gamma RT over M. Alright, so another important factor is about the longitudinal waves in solid. That's actually not important to this video and also not in the series video, but I just presented that equation if you need in case. V equals E over rho, so E is the Young modulus, rho is the density. So this is actually important in the case of the last topic of physics, which is the properties of matter and the usages when I am talking about the modulus, the surface tension and so on. But because it's actually a topic of waves, I am explaining here along with the other speeds of different media. Alright, to start with, the applications of sound waves. Sound as produced by different sources have different characteristics. Now for example, if you take the sound from a loudspeaker with some frequency, you may not hear the same sound, or you may not hear the same quality of the sound. What I mean by quality is the tune, right? So you can say that if you compare the sound from a piano or from a violin, you can say that although they may resonate with the same frequency, but the sounds may be different, and the intensity or the limit of sound you see in these two instruments may be different. So sounds differ from between different various instruments due to three main characteristics. They can be summarized into three main characteristics. One is the pitch, the second one is the loudness, and third one is the quality. So my intention of this video is to explain you about these three qualities and then explain the applications of sound waves as a whole. So to start with, first of all I will explain you what is meant by the pitch. So pitch is a term used to describe how high or low a note is being played by a musical instrument or sings to be. So you can say that when the pitch, so high frequencies produce high pitch note and low frequencies produce low pitch note. Now you can say that if the frequency of a particular note is 300 hertz, you can say that it has a high intensity. So you can see it here. So here you can see that the number of waves per unit time is less, so its frequency is high, so its pitch is high. And here the number of waves per unit time, so what I mean by unit time is the time range I am choosing from here to here. It's low as compared to this one, so its frequency is low, so its pitch is also low. So you can see here more, right? Now we can see if you take normal your sound, right, your sound speaking like this, and the sound from a loudspeaker, you can say that the loudspeaker is heard over a large distance and its intensity is very high. That's the reason because the frequency of the loudspeaker emittance of sound is high. You speak to some microphone or some instrument and that emits sound signals to the loudspeaker, which then resonates, actually vibrates with its air column, and then produces electric signals so that the sound is spread through the air. So its frequency is high as compared to the normal voice of a person. So since its frequency is high, the loudness is high, and thus the pitch is high. So the intensity and the amplitude of such a source can be defined as follows. Now you know that if you have some loudspeaker, you can not only hear now even your speech, human speech, you can not only hear, you can also hear the human pitch or the sound from a loudspeaker or sound from any other source, not in only a linear path. It actually spreads throughout. So if you are somewhere here, so say here's the loudspeaker, or here is the person where you are speaking. A person not only here, a person here, everywhere, he or she can hear the same sound, right? So it's very popular if you are going to some stages. In the case of political stages and so on, you can see when these people, right, they give speeches, you can hear over a large distance, not only the persons who are immediately in front of them, but also persons who are in back of them, and also in the sideways. So it actually maintains a spherical nature in which we are concerned about the radius from the source. So the intensity of some sound wave is actually proportional to the area, and since it's given as a power, we define the intensity of some sound wave as the energy per second per meter squared, or energy per second is actually the power or the watt value. So watt value divided by meter squared. So the intensity, the SI unit of sound intensity is watts per meter squared. So for example, you can take that now watts per meter squared is actually now the intensity is equal to power divided by area. So that's the reason as to why we get watts per meter squared. So you can say that I equals P by A. So if you take a simple example like this, in which you have a loudspeaker of power 20 watts producing sound to a certain area, the intensity of the sound at a certain area R from the sound loudspeaker can be written as 20 watts over 4 pi r squared. So 4 pi r squared is the area of a sphere of radius r. So it's in spherical in nature, not circular. It's spherical in nature because we don't want to. We are concerned about the 3D format, not the 2D format. When you consider the 2D format, it's circular in nature. But when you consider practical in nature, you want to consider about the 3D nature. So it's spherical in nature. So it's not equal to 5 r squared. It is equal to 4 pi r squared. So that will simplify to 5 over 5 r squared. So what's important here is that I is inversely proportional to A, or that the intensity is inversely proportional to area. So the distance you go, right? So if you increase the distance, say you have initially a distance of 20 meters from the loudspeaker, and you then travel away from the loudspeaker to a distance of 40 meters, the intensity decreases. So that's very evident in the case of practical examples. You may have seen that if you travel away from a loudspeaker or any source that emits sound, the sound waves that reach you diminishes. So since A is proportional to R, it can also be shown that I is proportional to 1 upon R squared. So actually I is proportional to 1 upon R squared, or I is inversely proportional to the square of the radius between these two objects, is actually the basis for the theory that I is inversely proportional to A. So that's it about the intensity and the amplitude of a sound wave that reaches a distance R from the loudspeaker is in the simple harmonic motion, and we can build up another relationship for the case of the amplitude. If the mass of the layer is m and the maximum velocity of this vibration is v, so if you take a simple part like this, a box or something like this, its mass is m and its velocity is v, you can say that the energy of this layer is the kinetic energy, because it moves with the velocity of v, so its energy is half mv squared. Now you know that these sound waves move in simple harmonic motion, they vibrate above the same place, and along with this they travel, so they are in simple harmonic motion. So you know that if an object is in simple harmonic motion or even circular motion, the velocity is equal to omega times a, right? So v is equal to omega times a. So the energy of the layer is half m times the 2 phi f times a, and you can simplify that that the energy of the layer is finally 2 times m times phi squared times f squared times a squared. So the intensity of the layer, so what's important here is that the intensity of the layer for a given frequency is directly proportional to a squared. So the intensity is directly proportional to a squared, and also you derive that intensity is directly proportional to the square of the radius between these two objects earlier, and from these relationships you can say that the amplitude squared is inversely proportional to the radius squared. So finally amplitude is inversely proportional to R. So another important thing that I have mentioned here is the concept of decibel. So what is the decibel? So decibel scale is a reflection of the logarithmic response of the human ear to changes in sound intensity. Now you know that sound intensity is very much low, so you cannot measure in the case of, you cannot compare different sounds in the case of minus values. So the human sound is in the range of 1 into 10 to power minus 12 and 1 into 10 to power something, right? So we call those the ranges. So they are always very minute values. So what we do is we take the logarithm of that, but when we take the logarithm it will be another minute value. So we have to take the we have to multiply that value by 10 as well. So we define not the bell is actually the first definition, and then we, since it is very small, we explained about the decibel. The sound intensity in decibels above the standard threshold of hearing. So I'll explain about what is meant by the standard threshold of hearing. Is calculated as a logarithm as follows. So I in decibel, or the intensity in decibels, is equal to 10 times the logarithmic ratio of I over I naught. So I naught is called the threshold of hearing. I is the intensity in which we are concerned about, right? So for example, if you assume an intensity of sound of 1.5 into 10 to the power minus 7 watt meters per square second, then the decibel value for such an intensity can be calculated as follows. So I is equal to 1.5 times 10 to the power minus 7 watt meters per square second, and I naught is equal to 1 times 10 to the power minus 12. So the value of I in decibels is equal to 10 log 10 to the base 1.5 times 10 to the power minus 7 over 1 times 10 to the power minus 12. So finally you can get a value that the value is 51.76 decibels. So that's about the decibels. So as I mentioned, what are these thresholds of hearing and what are the thresholds of pain? So what are these terms? The threshold of hearing is actually the lowest audible sound at a frequency of 1000 hertz, and it's actually is the minimum sound that you can hear. Minimum sound is which is evident, or which human ear can recognize. So that frequency is 1000 hertz, and the intensity for such a wave or such a sound is 10 to the power minus 12. So that's the minimum sound a human ear can hear, and the maximum sound that a human ear can hear is called the threshold of pain, or is the intensity of sound which makes a painful sensation to the ear. So that is about 1 meters per square second. So this actually varies between 0 decibels and 120 decibels. So this variation can be graphically explained as follows. So this is actually a complex graph of different sound sources. So you have the threshold of hearing somewhere here, around 0 here, and threshold of feeling around 120. So the human speech generally doesn't vary between 0 and 120. It's actually in a range which is very small here. So the frequency is somewhere here. So the human frequency is somewhat between 100 and here is 5000 hertz, 5 kilohertz or 5000 hertz, and the intensity varies between about 30 decibels to about 70 decibels, right? But in the case of music, you can see that different music sources from different sound sources, from example pianos, violins and the other sources, the sound pressure level or the sound intensity is much high. So it also has a high frequency, it also has a high intensity. So the audible range or the threshold of feeling and the threshold of hearing can vary as follows for any sound source. So this is actually graphical interpretation to explain that the threshold of hearing and the threshold of pain for human ear varies in between 10 to power minus 12 and 10 to power 0. So the second topic I have to explain you is about the quality of the timbre. So the quality of or the timbre of a note depends upon the waveform. So you can see here that if you take a flute, a piano and a trumpet, different wave patterns can be formed, different wave sound pressures can be formed with time. So flute almost has a very filtered or a very pure waveform, the waveform that we are just taking, the crests and the troughs. But the piano is somewhat unfiltered here. You can see that it is not even, right? Although these are even, it is not similar to this one. And the trumpet is the most uneven. So the quality of the timbre, we don't need whether it's even or uneven. The quality of the timbre depends upon this waveform. So two notes of the same pitch and loudness played from different instruments do not sound the same. Now you say if you sound the C note on a piano, on the flute and trumpet, they sound different sounds. Although their frequency is high, the sound pressure emitted by them is different. So that affects the quality. So for different sounds we have to use different instruments. We can't produce all sounds used in a piano, and we can't produce all sounds used in a flute or a trumpet. For different sounds, for at different frequencies, you have to use different instruments. So the quality depends upon our intention and our use or our perception of sound and what we want. So the sound we want to produce differs from instrument to instrument, and that makes up the quality or the timbre. And another important thing that I could mention in my previous videos is about beats. So beats had already been explained in a very small vein in one of my previous videos, but I made this part into this video because beats are actually a part of sound. Although beats vary for different frequencies, beats should always be defined for different sounds. So that's the reason as to why I included beats here, not beats in detail here, not beats in detail in another video. Alright, so what are beats? So if you consider two waves like this, I will take the same wave. So the first wave has a frequency of 40 Hz and the second wave has a frequency of 50 Hz. So the difference between their frequency is 10 Hz, and we call that difference to be the beat frequency. So if you actually combine these waves, you can find a combined wave like this. So in some areas you have the minimum displacements, which are analogous to the destructive interference due to these two waves, and some waves in some places you have the constructive interference, which have the maximum amplitude. So these areas have constructive interference, these areas have destructive interference. So at the areas of destructive interference, sounds can be heard, but it's in a very minute scale. Sometimes the sounds can never be heard. In the case of constructive interference, sound can be heard with the largest intensity. So beats are heard as a result of the difference of frequencies, but there should be similar frequencies. Now this can't be 40 Hz and this can't be 240 Hz. It should be very similar, at least a 10 Hz or 20 Hz difference. It's better if the difference is very small, and the number of beats you can hear is also large when the difference is very small. So you have to take two sound waves of very similar frequencies and you have to interfere with one another. So the beat pattern changes at a regular rate. So as I mentioned, when a constructive interference occurs, a loud sound is heard, and this results for a peak in the beat wave pattern here. Similarly, when the destructive interference occurs, the sound wave diminishes and sound sometimes can never be heard, right? So we can build up a beat frequency formula for this. So actually I explained that in the case of tuning forks and the resonance. So the reason as to why I mentioned the beats can be, now you can see that. So we have to use the form of waves and sound in which it has been described under the applications of sound. So if you have two tuning forks frequencies f1 and f2, which have cycles f1 and f2 cycles per second, and f1 and f2 are very close to each other. That means f1 doesn't exceed or by f2 by a large value, or f2 doesn't exceed f1 by a large value. A loud beat is heard due to the maximum resultant displacement, so that is the occasion of constructive interference from the two forks. After this, the vibration of air go out of phase, and again after some time t another beat is heard. So you can see that from this one. So after some time it goes out of sound, and then again a beat is heard, then it goes out of sound, again a beat is heard. So you can say that the number of cycles made by each fork in time t is f1t and f2t, right? So you know that the period is equal to 1 upon f1 and 1 upon f2. So the times between these, if the time is t seconds, then you can say that f1t minus f2t should be equal to 1, right? Because there is one cycle that is being heard within a time interval of t with two frequencies f1 and f2. So f1 and f2 is equal to 1 upon t. Now one beat has been made in t seconds, so that 1 upon t is the number of beats per second or beat frequency. So 1 upon t is the beat frequency, so the difference between these two frequencies amount for the beat frequency. For example, if you keep two objects of frequency 40 Hz and 50 Hz here, as you saw here, 40 Hz and 50 Hz, you can say that the beat frequency is 10 Hz. Alright, so that's actually the end of the explanation of different sound sources and the application of sound. So in the next video, I'll finish the topic of waves by explaining you about the Doppler effect. And thanks for watching this video, and see you soon.